Hello. In this video, we turn back to the very first topic in calculus, limits. We study some indeterminate forms and very powerful tool, the L'Hopital rule, how to solve limits. Remember that when we studied limits, so we didn't know anything about derivatives, right? Because the topic is limits, and then after that we consider continuity, and only after this we consider differentiability. Right? And now we know how to take derivatives, right? And we use this, we apply this to find limits. That is about L'Hopital rule. Okay, so what are indeterminate forms? If you have some limits, the first thing you need to do is just plug x0 into the function, right? Into the function. And if the function has the following form, 0 over 0, infinity over infinity, then we say yes, these are indeterminate form. Of course, in calculus 1, we already learned some techniques like dividing technique and rationalizing technique. Remember that? So let's recall them like dividing technique. Means if your function f of x is kind of fractional, px over qx, and then x0 is common 0, right? X0 is the common 0 of p and q. So that means you can factor p and q by x minus x0, and then you cancel it out. Like if you have the function 2x squared minus 1, right, over x plus 1, let's say that, when x approaches negative 1, okay? So, when you plug negative 1 into the function, you got 0, 0. So, negative 1 is common 0. You can factor the top. You have limit to x minus 1 times x plus 1, right? And in here you have x plus 1, x approaches negative 1. And now you can cancel this part. You get limit of 2x minus 1 when x approaches negative 1. And then you plug negative 1 into the function, you got negative 1 minus 1, and that is negative 4. So this is dividing technique, right? Sometimes you have another one. If you have infinity over infinity like this, you consider the limit of 3x squared minus 1 over 2x squared plus 1. X approaches infinity. And of course, this is the form infinity over infinity. So how to solve such limits? I have x squared in here, x squared in here. In order to solve this, I just divide the top and the bottom by x squared. I pick the term with the highest degree, right? In this case, x squared. Okay, so I have 3 minus 1 over x squared. We don't have x squared in here because we already divided, right? And of course, we divide the top and the bottom. I have 2 plus 1 over x squared when x approaches infinity. And now this term and this term approaches 0. So we have the limit is 3 over 2. Okay, so these two examples are pretty easy. But sometimes you have limits with exponential function and logarithmic functions. It's very rarely if we can't apply one of these techniques. Okay, so you might think, yeah, we need a new technique. In this case, we need to use the derivative. Let's talk about L'Hopital rule. Suppose that you have two functions f and g and both are differentiable. That means, f and g have derivative on an open interval a and b, okay? And that interval contains c, except possibly at c itself. And if the limit of f over g has the form in 0 over 0 at c, when x approaches c, and the limit of the derivative of f divided by the derivative of g is x, then the limit of f over g equal to the limit of derivative of f divided by derivative of g. So what does it say? It says, yeah, instead of finding the limit of f over g, if you have the form 0 over 0 or infinity over infinity, you might think about, you need to find the limit of quotient of derivatives. Okay? Of course, we have some conditions like f and g are differentiable, but, in this course, yeah, basically all functions will be differentiable, right? If we don't say anything about differentiability of such function. So the most important is, when you see a limit and you have fraction in the limit, right? You plug the point into the function, you got 0 over 0 or infinity over infinity. So you might think, yes, we can use L'Hopital rule by differentiating the top and the bottom. This is not the quotient rule. Not quotient, don't forget that. I taught this course several times, and sometimes students are confused with this. We differentiate the top and differentiate the bottom. We don't differentiate the whole f over g using the quotient rule. Okay, we have to pay attention on that. Let's consider the following example. Let's evaluate the limit of e to 2x minus 1 over x at 0. So you plug 0 into the function, you get e to 2 times 0 minus 1 over 0, and that is 0 over 0. Okay, so both functions are differentiable, as we know. X is, of course, differentiable, and exponential function is also differentiable. We can use L'Hopital rule, right? Let's try to use that. So how to write the solution? Okay, let's find okay, the limit of what? E to 2x minus 1 derivative over x derivative. X approaches 0. So, you cannot just write the limit of this guy equal to this guy right away. We don't have right to do that. The L'Hopital rule says these two limits are equal if this limit is x. Don't forget that. So we need to consider the limit of quotients of derivatives first. If the limit is x, we say yes, by the L'Hopital rule, the original limit equal to this guy. Does that make sense? So I don't write this limit equal to this right away. That is common mistakes I used to see. So I differentiate this, I will get on the top, I have 2 times e to 2x. We use the chain rule. In here I have 1, right? When x approaches 0. And now everything is good. I plug 0 into the function. I get 2e to 0, which is just 2. Then from now we say, yeah, by the L'Hopital rule, the original limit e to 2x minus 1 over x. X approaches 0 equal to 2. You see, only in the case when this limit is x. Don't forget that. So you need to consider that limit first. Alright? Let's consider the second example. The limit of ln of x over x, right? X approaches infinity. So now we have a function that involves logarithmic function ln of x. And when you plug infinity, right, to this, you get infinity over infinity. Not just plug infinity. Let's say you consider the limit of ln of x at infinity and x at infinity. Let's say that, okay? But you know, sometimes I say, yeah, just plug infinity, plug the point into the function. So in this case, yes, indeterminate form, and your functions are good. They are differentiable. So I may use L'Hopital rule, right? Let's find the limit of ln of x derivative over x derivative. X approaches infinity. So on the top you have 1 over x, right? In here you get 1. X approaches infinity, and that is just limit of 1 over x. X approaches infinity, and we know this is just 0. Now we can write by the L'Hopital rule the limit of ln of x over x. X approaches infinity equal to 0. Okay, so if you don't know L'Hopital rule, I'm not sure how to solve this limit, to be honest with you. It's complicated. Let's do one more example or a couple more examples, and then I can summarize in the form like comparison. So we will use that comparison in the future too. So, but we need to consider some examples, and we'll see, right? Another example, limit of x squared over e to the x when x approaches infinity. Again, right, this is indeterminate form, infinity over infinity. So, but the function x squared and e to the x are differentiable. We can use L'Hopital rule. I need to find the limit of x squared derivative divided by e to the x derivative when x approaches infinity. And this is the limit of 2x over e to the x. X approaches infinity. Because the derivative of e to the x is itself. But, you know, at this stage, we still don't see the limit, because the new limit has the form infinity over infinity, right? So that means we may use the L'Hopital rule one more time, right? We can differentiate one more time. So I write, that is the first step, okay? The second step, I need to find the limit of what? 2x derivative divided by e to the x derivative. X approaches infinity. And in here I see this limit is equal to 2 on the top and e to the x in the bottom when x approaches infinity. And this is what? This is 0. Because e to the x approaches infinity, right? As x approaches infinity. 2 divided by infinity, just infinity. Alright, so what does it mean? The limit of this equal to 0. So I write now by the L'Hopital rule, the limit of 2x over e to the x, x approaches infinity, equal to 0. So if I apply the L'Hopital rule for this, right? For this, I have the limit of this guy equal to 0. And then once I know the limit equal to 0 right here, right? I apply the L'Hopital rule one more time to get the limit of this guy. You see, so we need to apply the L'Hopital rule twice. From now, I can write again by the L'Hopital rule, the limit of x squared over ex here, x approaches infinity, equal to 0. So we finished the problem. Okay. All right. You know, sometimes some people can write like this. They have the limit of x squared over ex, x goes to infinity, right? This is infinity over infinity equal to limit of x squared derivative over ex derivative, x infinity, and this is to limit of 2x over e to the x, x infinity, and you still see the form infinity over infinity. You differentiate one more time, you get limit of 2x derivative over ex derivative, x approaches infinity, and you get limit of 2 over e to the x, x approaches infinity, and you get 0. From here, the limit of this guy is equal to 0. I will tell you this, yeah, you know, I don't encourage to write in this way, okay, because you know L'Hopital rule can be applied only in the case when the limit of f derivative divided by g derivative is x, only in this case. Does that make sense? So we cannot write, you know, the whole chain, because you don't know, right? You don't know in which step the limit does not exist. Does that make sense? Now we already have two examples between polynomials x squared e to the x and logarithmic function. Okay, look at this. You have quotient ln over x. When x approaches infinity, the limit is equal to 0. 0. What does it mean? That means when x approaches infinity, the function ln of x approaches to infinity slower than x. Okay, much slower than x. And this guy also equal to 0, right? Equal to 0 right here. Again, this says polynomials x squared approaches infinity slower than e to the x. You know, if you change x squared by x to the n with any power n, you still get 0. Because you apply the L'Hopital rule several times, right? N times, let's say that. You get 0 at the end. So that means any polynomials approach infinity slower than exponential function. So what can I say from these two examples? When I consider ln of x, polynomial and exponential function, I write polynomial x to the n is slower than e to the x. And if you have any power in here, so let's say m, this is still slower than x to the n, where m and n are natural numbers. And this happens at infinity. I tell you, this is very important because we will use this in the future. We study series, we study different criterions for series to converge. And many series involve logarithmic function, exponential, and then polynomials. Okay? And I will not repeat this again, right? We need to use comparison at infinity. Okay? Comparison at infinity. I remember we have this idea when we study Calculus 1. Calculus 1. When we study limit of psi of x over x. So I hope you remember this limit, right? It's very famous one when x approaches 0. We know that this limit is equal to 1, right? Is that correct? The limit is equal to 1 means that psi of x is similar to the x at 0, because you consider at 0 right here. So the limit is 1 means, two functions are similar. That means one can be replaced by another, right? So I can replace sine of x by x. That is the thing. Because they are very similar. They are very close at that point. Does that make sense? So, this is how we can compare two functions at some point. And I remember that, last year when I taught Calc 1, I asked my students to solve the following limit, like sine 2019, right? X minus, let's say, x squared. In here we have like, okay, let's say x, x, let's say that, x approaches 0. With x squared and x, everything is good, right? And say, yeah, this is the limit of sine of 2019 x over x, and then minus x when x approaches 0. With this part, everything is clear because that is 0. But with this part, you might think, yeah, we use this similarity. You get, limit of what? Of x 2019, right, over x when x approaches 0. And that is the limit of x 2018, right? X approaches 0 and you get 0. You see, it's pretty easy, right? But the idea is important, similarity, okay? Don't forget that. In the previous section, we studied this limit. Actually, we applied this limit when we study compounded interest. I hope you still remember that. Without proof, right? We accept that. But now, we know the Lobton rule. Let's use that rule to find this limit. And if you pay attention, when you plug infinity to this function, you get 1 plus 0 to infinity. So we have the form 1 to infinity. Okay? So, for such function, you would like to put y equal to the limit. Okay? We suppose that the limit is x, and that is equal to y, or a, or whatever you want, right? But let's put that equal to y. Now, the limit and the function ln, remember that the function ln is continuous. So you may apply this function to both sides of this limit. Okay, so you have ln of y equal to limit of ln of 1 plus 1 over x to the x approaches infinity. And ln is very good function in the case that if you have power in here, you can take the power down, right? So this is equal to the limit of x, ln of 1 plus 1 over x. Here, x approaches infinity. Look at this. This is interesting. Now you plug infinity into this function. You get infinity times ln of 1, which is 0. So this is the form infinity times 0. Right? But we just learned infinity over infinity and 0 over 0. And now we have infinity times 0. So how to get one of these forms? It's pretty easy. I think that is important, so I would like to write that separately, okay? Look at this. If you have infinity times 0, you want to get infinity over infinity, no problem. You write in the following form. Infinity times 1 over infinity. Because 0 is kind of 1 over infinity. You see that? And if you have infinity times 0, you want to write as 0 over 0, no problem. You write 1 over 0 times 0. Because infinity is kind of 1 over 0. You see, that's how we can convert this form into one of the forms we know with indeterminate forms. Okay, let's consider in this example. So this is infinity, this is 0. You want to get one of the forms 0 over 0, infinity over infinity. So you need to decide. You want to divide by x or you want to divide by 1 by ln 1 plus 1 over x. Let me write out two forms and then we will decide together. So I might have one of the following. The limit of x approaches infinity, ln 1 plus 1 over x divided by 1 over x. You see? So in this case, you have 0 over 0. Another way is limit x approaches infinity, x divided by 1 over ln of 1 plus 1 over x. In this case, you have infinity over infinity. So, in order to use the L'Hopital rule, we need to differentiate. Is that correct? Differentiate. But which function is easier to differentiate? If you differentiate this on the top, everything is good. This function is pretty easy. For this, yes, it's easy. But for this guy, yes, we might have trouble, right? We might have trouble. And each time when you differentiate this guy, the function ln is still there. But for this form, you differentiate one time, ln will disappear, which is good. Does that make sense? So when you see ln and x, yeah, you need to rewrite in this form. You just try to keep ln on the top, so it is easier for us to differentiate, right? So let me choose that. I write here limit of x approaches infinity. In here I have ln 1 plus 1 of x. In here I have 1 of x, right? And I need to consider this is 0 to 0. I need to find the limit of ln 1 plus 1 over x derivative over 1 over x derivative x approaches infinity. Okay, let's differentiate. On the top, we need to use the chain rule. So I need to differentiate. I need to write 1 plus 1 over x derivative over 1 plus 1 over x. You see the chain rule. And in here, I have negative 1 over x squared, right? X approaches infinity. So let's write here limit of 1 derivative is 0, 1 over x derivative is negative 1 over x squared. Let's keep writing like that. And here 1 plus 1 over x, okay? Everything divided by negative 1 over x squared. X approaches infinity. And you can see, actually, these two guys will be cancelled out, right? Because you take the whole thing in here, you divide by this, right? So you just, this part will be cancelled out. And at the end, you have, I write here, limit of 1 over 1 plus 1 over x when x approaches infinity. And that is 1 over 1 plus 0, which is 1. All right, what does it mean? That means we have that this limit is 1, okay? And by the L'Hopital rule, the limit of this guy is equal to 1, right? So what does it mean? Look at this. Let's go back. That means this limit is equal to 1, right? That means ln of y is equal to 1. You see that? Ln of y equal to 1. And from here, since ln of y is equal to 1, you get y is equal to e. So what we have done, we proved that the limit of this guy is just equal to 2e. You see, it's a long way, but we have some good ideas in here. Does that make sense? So we learn how to convert the form 0 infinity into one of these forms. Okay, and it really depends on the functioning here, ln on the top or ln in the bottom, and then you just differentiate everything and apply the L'Hopital rule. All right, I hope you still remember this function, x to the x. We met this function when we study applications of logarithmic functions. Like if you have function y equal to x to the x and you want to find the derivative, right? So we need to apply ln of y, we have x ln of x, and then you differentiate this function easily, right? And now we use the same idea like in the previous example, and actually that idea was considered in this example. Okay, so I put this equal to y, and again I apply the ln. I have limit of ln of x to the x. X approaches 0 from the right. And again, right, we can take this out here. So that is the limit of x, ln of x, when x approaches 0 from the right. And when you plug 0 into this function, you get 0 infinity. 0 infinity. And like previous example, I will keep ln on the top because I will convert this to the form ln over 1 over x. Right? So I have this limit is equal to, not yet, we have the form infinity over infinity, right? And then we need to differentiate. Okay, let's find limit of ln of x derivative over 1 over x derivative when x approaches 0 from the right. You get what? You get the limit of 1 over x on the top, and here you get negative 1 over x squared when x approaches 0 from the right. So you divide by 1 over x squared means you multiply by negative x squared, right? Just multiply by the inverse. So you get, x squared negative divided by x. X approaches 0 from the right. And this is limit of, okay, let's say minus in here, limits of x. X approaches 0 from the right. And you get 0. Perfect. What does it mean? That means, ln of y equal to 0. Right? Ln of y equal to 0. Or y is equal to e to 0, which is 1. You see? It's pretty interesting, right? Pretty easy. In the textbook, you might see the following example. Limit of psi of x to the x. X approaches 0 from the right. So how do you think? Can we write this limit is just equal to limit of x to the x when x approaches 0 from the right? Why? Because of this. And we just talked about that psi of x is similar to the x. So you can replace one by another. Make sense? By doing so, sometimes you may avoid working with trig functions. Right? Let's move to one more example and then we finish today's lecture. That is the form infinity minus infinity. So if you see the form infinity minus infinity, what to do? Here's example. Limit of 1 over ln of x minus 1 over x minus 1. X approaches 1 from the right. And when you plug 1 into these functions, you get 1 over 0 minus 1 over 0, right? So this is kind of infinity minus infinity. For such situation, the only thing I can do is just multiply or just try to get some kind of, more compact form of the function, because you have two terms in here, right? So let me compile them together. I have x approaches 1 plus. In here I have x minus 1 minus ln of x, and I have ln of x times x minus 1. And this form is already better. Why? Because when you plug 1 into the function, you get let's say 1 minus infinity, minus 0 divided by 0 times 0. Okay, whatever, but you can see that is 0 over 0, which is good. We know 0 over 0. So that means sometimes if you get the form infinity over infinity, you might convert to the form 0 over 0 or infinity over infinity again, right? And we can use the L'Hopital rule. Okay, so let's use the L'Hopital rule for this function. In order to do that, I need to find the limit of x minus 1 minus ln of x derivative divided by ln of x times x minus 1 everything derivative x approaches 1 plus. So let's differentiate this. I get limit of 1 minus 1 over x, right? And here I need to use the product rule. ln of x derivative is 1 over x times x minus 1 plus ln of x times 1. So I don't write it, okay? When x approaches 1 plus. All right, so what do we get? We have 1 over x here. Let's write that in a more beautiful way. So I get, right, limit of x approach 1 plus. On the top, I have x minus 1 over x, right? In the bottom, we have x minus 1 plus x ln of x over x. And you can see we can simplify x, right? That is limit of x minus 1 over x minus 1 plus x ln of x when x approaches 1 plus. All right, so again, you plug 1 into the function, you get 1 minus 1 over 1 minus 1 plus 1 times ln of 1, which is 0 over 0. So we need to apply L'Hopital rule one more time. I need to find the limit of x minus 1 derivative divided by x minus 1 plus x ln of x derivative. X approaches 1 plus. You see, we need to differentiate one more time, right? And you get on the top just 1. In here you have 1 plus x derivative is 1. I have ln of x, and then plus x times 1 over x, right? X approaches 1 plus. So I simplify this part. I will get equal to limit 1 over 1 plus ln of x plus 1. X approaches 1 plus. And you plug 1 into the function, you will get 1 over 1 plus 0 plus 1, which is 1/2. Perfect. We are almost done. So the limit of this guy is equal to 1/2. By the L'Hopital rule, the limit of this guy is also 1/2, right? And if the limit of this guy is 1/2 by the L'Hopital rule, the limit of this guy is 1/2, right? So the original limit is 1/2. Again, in this case, we need to apply the L'Hopital rule twice. Okay, so I hope you can write it for yourself. But you know, the main idea is if you have such function, try to convert to one of these forms, and then use the L'Hopital rule. Okay, so basically in this video we did a lot of examples involving Ln, logarithmic functions and exponential function, and you see L'Hopital rule is very powerful rule, right? So, we need to use that. And I repeat again, right? There is a very, very useful observation right here, which I call comparisons. Let me see, where's that comparison right here. So the comparison and L'Hopital rules are very important rules for the future in this course when we study series. So I hope that you do this pretty well, and I bet you will not have any problems when you study series. Okay, so thank you for watching and see you in the next video.